Okay, so then welcome to the last session, the last afternoon. So we'll talk about linear response theory, about excited state properties, how we can calculate excited state properties now under strong light matter coupling in these optical cavities. And in particular, then the method we are using to do that, to calculate these properties, is using a density function theory, so QDFT. So then I will first review the linear response theory of regular DFT. So if we have just electrons, and then once we understand that, we will move on to how we calculate that. So we will also be using the octopus code in this set of exercises. That will be the first step. And then from there, once we have the basics, we can move on. So we add complexity. We add the photons, the interactions of the electrons to the photons. So then we move from DFT, density function theory, to QEDFT. We will look at the linear response theory there. What is different between DFT and QEDFT? How will the linear response theory change? And then again, we will go back to the notebooks. We will use octopus. So the linear response theory of QEDFT is also implemented in octopus. So we will have a few set of exercises. Strong coupling, we will look, Rabi splitting. How can we get now Rabi splitting inside optical cavity for general systems? So here we will look at molecular systems, finite systems. And then we will also in the end make a connection to what we talked about on Wednesday, what Mark and also Simone introduced, the macroscopic QED framework, right, where we use Maxwell solvers to describe general arbitrary electronic environments. They can even be lossy, as complex as you wish. And then how can we interface such general electronic environments with ab initio methods and then with the QEDFT. So what do we have to do to input the environment correctly into our DFT simulation? So this will be then towards the end of this. So, but first I have some slides, so we can go over that. So first, right? So first we forget about what we learned throughout the school. So we forget about the strong light matter interactions. So we just think about electrons. We want to access excited state properties of electronic systems. So how can we do that, right? And one thing, if it's just electronic properties, one spectra, which is measured often in experiment, is absorption spectra, right? So I have one example shown here. So this is just a set of sodium, a dimer, and then there's some clusters. And then how can we compare? So if we get an experiment, right, they measure some peaks. So this can be homo-lumen transitions, for example, or other types of excitations in the systems. How can we compare these experiments now with our first principle method? So for example, let's say I run a DFT calculation. How do I get access to the spectra? How can I do that? And this is typically done via the linear response framework. And then there's a whole community around that, which is called computational spectroscopy. So looking at spectroscopic quantities, spectra, and using ab initio methods now to simulate them. And generally how we understand the linear response is that you think about a system. So like one system which is shown above here, maybe it looks like a cavity, but I don't think it's meant to be a cavity. It's just some random system, some material. Now what you do is that you shine a laser, you kick the system, and then you look at the response of the system. And then the question is, how can we describe that with ab initio methods? So that's okay. So one thing I also wanted to show here is like that's actually okay. I forgot to put the year, but I think this is from the 2000s, so quite a bit of older years, maybe 20 years ago. But already there you see that the levels of the lower row is experiment, and then the upper row is using density function theory, or here in particular time-dependent density function theory. And then you see that already on that level it does agree quite nicely. So most of the peaks you are able to capture. And then also the spectrum becomes more and more complicated the more atoms you have. So you see a richer structure of the peaks, but you see that overall the first principle methods here is able to simulate the systems successfully. So this gives us a hint that first principle methods, in particular time-dependent density function theory, are good tools to calculate such spectra or such properties in general. So we'll come back to that later too. Okay, but then, okay, I was already mentioning that. So how can we understand linear response, right? So what is the linear response, or more generally, a response of the system? So one thing, or the one idea, or one way to see it is really what I was already mentioning, that in a sense, okay, so I call it here, you perturb the system or you tickle the system slightly somewhere, right? So what we do here is we tickle the system at R prime, T prime, and then at a later point in time, we observe, so we do measurement and then we observe how the system responds to that. So already there you see that the response could be non-local. So you could kick the system somewhere else at R prime, and then you ask for the response of the system at a different point in space. So in this sense, it can be non-local in space, but at the same time, it can also be non-local in time. So you can kick the system here at time T prime, maybe that's 0 if you want. For simplicity, could be T prime, could be 0. And then you ask the response at a later time T. So there's non-locality already visible here. And then in practice, what we do, if you want to do absorption, one way to tickle the material or the molecule is to use lasers. So we shoot lasers on the molecule. And then the response here would be, for example, we could record the dipole moment, how the dipole moment evolves. So what you could do is you kick your system with a laser, you shoot a short laser pulse, and then the system will get excited and it will start to oscillate. So the dipole moment will fluctuate. There will be a fluctuation in dipole moment, and then what one can do is that one records this oscillation of the dipole moment, and a Fourier transform of that oscillation of the dipole moment gives us exactly the excitation energies and also the amplitudes of the excitations. And yeah, so the whole framework is called response theory. Typically, you can get away, or okay, it depends on the problem, but for absorption, for example, you can get away with the lowest order response. It's just that's called linear response theory, just in terms of nomenclature. Okay. And then you also wanted to just to make get everyone on the same page what we're going to do in the next few minutes. So what are the learning objectives? So I already mentioned, yeah, so we first to talk about just electronic systems, just to get linear response theory. So we get familiar with linear response theory. So we will look at generally linear response theory for electronic systems, in particular in the context now of density function theory, in particular in terms of densities and external potentials. I will get to that. And then the framework itself is general, so we get equations, but then how to turn these equations into something useful, into a spectra on the computer. So there's different ways to do that. Particularly what we want to do here is we use a frequency domain description, which is then what we call, so we have to solve this equation, which is named after Mark Casida, the Casida equation for TGTFT in this sense. So this is what we want to do first. And then this equation we can solve with Octopus code. So that's one example on that. And then once we have that, we can move on to the more interesting problem, okay, or the topic the school is about, right? The QD systems, where now electron and photons are coupled. So then we can see what changes from regular electronic systems in terms of linear response theory. So if we put these systems inside oblique cavities, how do we have to change the framework? And then also this Casida equation, it will change. So how do we change these Casida equations now for light matter coupled systems? And how do we solve it? And then in terms of exercises, in terms of these notebooks, we first look at electronic transitions only. So that's, of course, this will give us, so this gives us information about the electronic structure, which we want to calculate, which is, and also here helps us to learn more about linear response theory. But it also serves another purpose, because now if we want to couple the cavity, right, the question is where do we have to couple to? And then if we think about Rabi splitting, we want to split something, we want to split one peak, so where does this peak lie? Right? So first we have to calculate the excited state spectrum, or in this case, the energy specifically, then using just outside the cavity, just for the material or the molecule. And then once we know the spectra, we can think about how we have to change, or how we, if you want, how you have to design your cavity to see interesting effects. And then one effect could be you could try to split your peaks. You can or hybridize the peaks. So Rabi splitting, right? For that, we need to know the frequency where we have to put the photon mode. That's the first example for now with strong light matter coupling. Just in this first case, we'll just use a single mode, just a single photon mode, couple that, see what will change. And then we can move on to, I call it here realistic cavities. Where we can also then talk about strong coupling effects. And these relativistic cavities, then practice what we do in our simulation is that we have to include more than just a single photon mode. So then we will actually go back to the exercise which we did on Wednesday on the macroscopic QED, and then pick one of these examples, which you guys solved already in terms of notebook. And then we will add a little bit such that we create the output file. So we call it the photon mode file, which has all the information about the different photon modes, which we want to include in our first principle calculation. And then we take this photon mode file and interface it with the octopus code or first principle code, such that octopus will read in this external photon mode file, which has been simulated with macroscopic QED, and then use that in the, so here if we solve this Casita equation, we will use it in our Casita equation simulation. Okay. And then there's one more example, so depending on how fast we go, or maybe if you guys have some time on the weekend or in the next weeks. And then, so that's one example where we simulated natural lifetime. So that's where we put a molecule inside a one-dimensional optical cavity. We include as many modes as possible, and then you see the natural line width of your transition. So we can also look at that. So that's at the end of the notebook if you look at the notebook. Okay, and yeah, if you guys have any questions. And this is also meant to be a bit interactive, so just let me know. Okay, so then let's start with just a little bit of theory, or as much theory as we need. So yeah, what is the linear response of a system, right? So I was mentioning, so what we do is we want to kick the system. So maybe we have our system. Initially, what we do is we prepare the system in the ground state, and then we shoot a laser, right? So then if you think about expectation values, if we start with the ground state, right, at initial time, t, okay, I call it initial time here t naught. The observable we're interested in, so this could be the dipole moment, for example, in our system, is just the expectation value with the ground state. Right? So let's say alpha is now the dipole moment. Now what we do is that we do apply this time-dependent perturbation with maybe some potential like that. Where now beta is how this could be the dipole moment, for example. Here it's more general, could be any operator. And then so this could be the electric field. So if F is the electric field, and then we couple electric field to dipole moment, and then the shape of your laser pulse, right, would be in the F of t. So this could be, for example, a kick initially, or you apply some Gaussian around t naught here, something like that. And then, of course, the system is initially in the ground state, but now we have an external potential. We perturb the system at time t naught. And then, of course, all observables, because the wave function will be time dependent, also the observables will become time dependent. So that's the only way how it can be, right? So at time t, okay, I think this is flipped. T should be larger than t naught. Or observable becomes time dependent. And then if the response is, if it's just a short pulse, for example, what we can do is that we can write the response of the system in terms of powers of the field here, such that if we subtract the initial state, the initial alpha naught here, this would be the change with respect to the ground state. So then what we call is that we call the first one first order, second order, and third order, and so on. And then if the pulse is short and weak, the first order one will be the dominant one. So that's, in a sense, the limit we are working on. Of course, if you have an arbitrary pulse here, a long pulse, it has maybe a very complex case. The response you will have all orders which will contribute. So then it will be much more non-trivial. But for short and weak pulses, the first order, the linear response, will be the important one. And this is the response which will allow us to calculate things like absorption spectra, for example, on the electronic level, or infrared spectra, for example, if the response was for the nuclei. Okay, and then more formally, what we can do is that if we, okay, so that's I think, okay, I'm not sure. So the acetylene molecule. So generally we do that, we probe the system and then we detect at some point, as I was mentioning, and then maybe you kick the system at R prime, T prime, and then you ask the response at R and T. And formally how we can connect this, so this now goes directly to density function theory, or more specifically the time-dependent density function theory, is that we can connect now here what we want to have a connection in DFT. There's a one-to-one correspondence. This was discussed already yesterday when DFT was introduced, between the density and the external potential, right? So the potential is now the perturbation and the density. So there's a one-to-one correspondence. So these two variables are the fundamental variables in the density function theory. And now what we do, so that's just like a mathematically, right? We can just write a formula like this. What we now want to have is that we have a perturbation, we apply a perturbation, and want to connect the perturbation now to the density, so we call it here the response. And then what we can do is that formally you can write this down, that there's something in between which connects the two, which is the response function, which gives us then all information about how the system now, here the acetylene molecule, reacts to an external perturbation and gives us back the response, the density response. So that's just very general. And then in practice, there's different possibilities to solve these equations. One thing in TD-DFT, which is the maybe most straightforward, at least conceptually approach, is that we can actually do an explicit time evolution. So we could actually set up the system like that. The molecule is initially in a ground state. So we do first a ground state calculation. This will be our initial state. And then we explicitly apply a pulse, right? So we could apply a pulse. So the V now, the external potential would be this pulse. Could be short. Okay, maybe you wanted to put a Gaussian, a small Gaussian, narrow Gaussian around initial time, and then you just propagate the system. So the system will, the pulse will hit the system, you couple to the dipole moment, and the system will start to oscillate. There will be an oscillation of the dipole moment, and then you can record the oscillation of the dipole moment, take a Fourier transform, and this will be your spectra you want to look at. This will be the absorption spectra. So that's one way to do it. You can do that. We call this time domain, so solving it in a time domain. But there's also a different way to do it, and the different way is to solve it in the frequency domain. The nice thing here is that we map this problem onto an eigenvalue equation. So okay, I will get to that, but we will have to solve this, what is called Casida equation. So that is a matrix equation. And then you just diagonalize that matrix, and then the eigenvalues are the energies, so the poles of your response function. And the eigenvectors give you information about the amplitudes. So that's an alternative way. And there's also a third way, which is called Sternheimer equation. So you guys could also look into that. And then depending on the size of the system, so generally if you have a small system, where only a few orbitals are contributing, a few occupied, so with orbitals I mean a set of both occupied and unoccupied, maybe the Casida equation is more favorable in terms of scaling, because in the end, the bottleneck here is that you have to diagonalize a matrix, and we can only diagonalize matrices of a certain size because of polynomial scaling. However, here it's convenient because we directly get access to different properties. So that's why this, I mean, we'll get to that, but that's why solving that is a good idea if it's possible. While the time domain might be more favorable if the system is very big, such that constructing that matrix, if you have many occupied orbitals and many unoccupied orbitals, which you have to consider, then maybe the resulting matrix is just too big to diagonalize. Then what you could try is that you could aim to solve this in a time domain. And then the way to do it would be an explicit TD-DFT simulation. So there's always trade-offs. And then depending on your situation, it might be more favorable to solve one or the other. And what we will do in this example or in this afternoon session is that we will use the Casida equation. But everything else also applies straightforwardly to the time domain. Questions? Yeah.
Also regarding the earlier slide, is there some beta for which the second order and so on vanishes, so first order becomes exact?
Well, I mean, it could be that the even orders vanish due to symmetry, but otherwise, yeah, it's just in the limit that the pulse is weak and short. Only the first order will remain. But of course, it's just an approximation in the sense that so I don't think there's a way to only get the linear order in the full exact propagation. Yeah. Okay, but that what's one thing is symmetry could be employed, and then could be that the second order response vanished, only the third order. If you have inversion symmetry, I think that would be the case. Okay, so I have maybe 2 or 3 slides more on theory. So here, this is the connection now. So I was mentioning here the connection between the density response to, okay, so here there's typo, to there's the potential missing, delta V is meant to be. Okay, so it's here. This guy is supposed to be here too. And then the connecting, or so the quantity which connects the two is the response function. So here the chi first order response function. And then in the DFT way okay, there's different ways to represent that. So one way to do it is in terms of the language of DFT, where everything is based on this one-to-one correspondence between density and potential, right? So these two are the ingredients on our DFT or TDFT. And then you can write down something like that, where now the density response, you have an additional object here, which you expand. And now you just write down, okay, you have delta n, which is then equal to delta n again, but then you expand delta n around or with the potential here. So then in this sense, the response, this response function chi r, rt, r prime, t prime, is delta n vn. So the response of the system under an external potential, and what is the resulting density. So that's the response. And then, yeah.
One of the things I was asking before about whether you can get the linear term only in TDDFT, not by propagation. There is one way which is not optimal to do. Yes. What you do is you do calculations for different strengths of the applied field. And then basically you take the spectra and you plot this attention of the strength. And then there is one term that goes linearly with E, another that goes linearly with T square, another that goes with EQ. And this is completely the brute force approach to get the linear, quadratic, and octupole response of this. We would not do it that way because it's not convenient, but that's something we could do.
Yeah, but he was asking if there's a situation or material where the linear response is the only response. So there's no higher order responses.
No,
which I don't think that's.
I don't think that's.
Yes.
I think maybe for the harmonic oscillator.
Yeah. Okay. Okay.
Exactly. Because for that case, you can solve the Lorentz model, and then all you get is a term that is going with E. But that's the most boring.
Yeah. Well, there will be one transition, no, which may know already.
Because the problem there is that the spectrum of the harmonic oscillator has always the same energy differences. So whatever you do, exactly. Inside the same thing.
Plus there is Conn theorem. There's only one excitation.
Yeah.
Yeah, exactly. So if the system is very harmonic, and just, yeah. Okay, but then connecting to that, right? So here, that's all. It's just there's no DFT in this sense. There's no approximations. So that's exact. So let's say we would do an exact simulation. Maybe we have a way to do that. We could calculate the response function exactly. But now that's not how we do simulations, right? So we want to use the density function theory. And then in density function theory, what we do is that all simulations we do in the end, we do in the conjunct system, in the KS system. And then for the conjunct system, we have the effective potential, the Vs here, which is given. So the conjunct potential is given by a sum of different terms. So here I divided it like this. We have the external potential. So that's just our pulse we apply, or maybe also some contributions from nuclei. But then we have additional terms. One is the classical one, R3. That's simple. And then everything which we don't know is shuffled into exchange correlation potential. So that was already discussed the other lectures on DFT. Okay, or okay, if you have photons too, maybe there's a correction too for the photons. But then all approximations in the end, and also the quality of our calculation, depends on how good of a job we are doing to approximate this guy, right? The potential, the exchange correlation potential. So now what we want to do to connect this linear response theory to DFT, so we need to make connections of the interacting response function, the chi-r, to quantities which we can calculate with a Concham theory or with density function theory. Right? And this we can do in the following way, which is written here. So the interacting response function, the full response function in the system, can be expanded in terms of, so that's just the Concham response function, just a response function of our Concham system. So we have this guy, and then we have additional contributions now, Concham function of the non-interacting systems. Here, that's still the many-body response. And then in between, so this is these quantities which are called kernel. We have to put the kernel, and then we have now different contributions of the kernel. So we have one part which is again the classical part. It's just the derivative, the functional derivative of the Hartree potential with respect to the density. So that's just the Coulomb potential. This gives us just the Coulomb potential. So that's simple. We can do that. But then this is the part which we have to derive, or we have to put our approximations. So that will depend on the level of theory you're using. So if you're using, I mean, probably nowadays 90% DFT correlations on the PBE level. If you use PBE, if you plug in PBE here, if you want to do a response calculation, you would have to calculate the kernel for PBE, and then you would plug in your PBE kernel here, and then solve this equation on the DFT level. So then your potential is the PBE for Vxc. You just have to take the functional derivative with respect to the density, and then plug this in. So, but for this we have libraries. So libxc, for example, can return that. But this is where all the approximations have to go into. And then I was mentioning the Casida equation. So that's the equation where we map this problem to. In the frequency domain, we can map the problem of these excitation energies and amplitudes onto an eigenvalue equation. So that's what I was mentioning. The eigenvalue equation looks like this. We have different elements here. So okay, here we have just two, A and K, and then the omegas will be the eigenvalues, and then these will be the poles of our response function, or the position where the peaks are in the spectra. And this is the way how we calculate it. So just A, so A epsilon. So now we have A and I. So these are occupied and unoccupied orbitals. So you already see here that we will also need unoccupied orbitals in our simulations. So we'll get to that later when we use Octopus. We have to actually do two calculations. One calculation is where we just convert for the ground state. If you are on the PBE level, for example, it's for the ground state, you just need occupied orbitals. So you only need to consider the occupied orbitals in your simulation. But then if you want to construct this matrix here, we also need at least some unoccupied orbitals. And then in the end, you see, so we take differences, energy differences. So these are just differences between Concham orbitals of these unoccupied orbitals. And then, so it's just the A, and then the A also includes the K. And this is then the more, so that's just energy differences between Concham energies. So that's very simple. But then we see that these energies between Concham orbitals is already not sufficient to get the excitation energies in our system. We have to go beyond that. And this is then where the K comes in. And then for the K, we have to take these, again, we have these orbitals. And now we have to, so here the kernel appears again. So we have to take this integral. So here we have 4 orbitals here. So we have again occupied and unoccupied orbitals. And then we have to sandwich it. So that's just the classical part, the Hartree part. And now with our your favorite exchange correlation. Here's the kernel, the favorite exchange correlation. Sometimes you also see in literature, people talk about, for this Casida equation, they talk about RPA calculation, just means random phase. And this means they neglect any exchange correlation potentials, contribution. So you can also do that, of course, in approximation, but then you already get corrections to just the energy differences in the Concham energies. Okay. Yeah, and this just maybe again as an advertisement for the method for TDDFT, how well it performs. So that's okay. That's a benzene molecule here. So that's okay. So that's what I was mentioning. So the simplest thing you could do is okay, let's say you do your ground state calculation, right? So you get your maybe a few electrons, and it looks like this. So these are all quantum energies here. Let's call them epsilon ks, right? And then one could just say, okay, the excitations of the system, they are very simple. So just what I want to do is that I have to promote here one of the spins up, and then the energy difference between these two, between the maximum, so okay, the HOMO and LUMO, the highest occupied and the lowest unoccupied orbital, just the delta, right? So just the delta, and then we say just this delta here would be the true excitation energy in our system. And so one could do that. That would just be ground state calculation. So that's very fairly straightforward, right? So this is what they do here. So they do they call it LDA simulation. They look at the first peak here. Okay, in this particular case, they see that this difference in energy is around 5 eV. But if you compare to experiment, you see that experimentally the first transition, so the HOMO-LUMO transition, is around 7 eV, right? But this is already mentioning. So if you go back to the Casida equation, this means exactly that. If you just consider the first term, just the energy differences of the quantum energies, we just have the first term, and then we neglected the second term. But now we can do better. So we can also include the second term. And this is then exactly what they do here for this system. So that you see, if you do that, the K actually shifts this peak. So it shifts it to higher energy. And then it's still on the LDA level. So the function is still the same. But now we use also LDA for the kernel, for this kernel found in Casida. And then you see you get quite close actually to the true peak. And then there's one paper that's for Uncle left, but this one, one of the first, but that's the first octopus paper, where actually I think it's the same system, also benzene molecule, and actually they also use TDDFT. So then the experimental line here, the experimental data is here in the solid line, and then you see, so they have here just in the C direction and average, and they get very close actually with TDDFT on the LDA level on the experimental result. So I think the difference between these two calculations is just how many excited states you include. So if the more excited states and the finer the basis set or the grid, the more accurate you choose your grid, you can, for this system at least, get very, very close to the exact or the experimental resolution. And then actually, interestingly, not only the HOMO-LUMO excitation is very well described, but also all this tail here is rather well described by TDDFT in this case. So it does work for many cases. Okay, so that brings me then to where we are in terms of simulations, or the simulation which we have to do. So you guys have already experienced now. You are already experienced users of the Octopus code. Maybe some for one day, but today's second day. So then I think most of you already use this calculation mode. So in Octopus, there's the different modes of the calculation. GS stands for ground state. So I think the calculations you did yesterday, you were using this calculation mode. So you calculate the ground state. So if you want to do such a linear response calculation, now you have to do 3 calculations, not just one. So let's say you did already your calculation for the ground state. You have converged your density. Now you have to do a second calculation. This is because the reason for that is what I was just mentioning, that we not only need the occupied orbitals, but also information of unoccupied orbitals. So there's a special calculation mode, which is called unoccupied. It just reads in the ground state, and then you can specify to converge a few more unoccupied orbitals. So that's this mode. So you have to do a second calculation. We call it the calculation mode unoccupied. And then once you have these two, we can do finally our linear response calculation. So here we use the run mode Casida. Okay, calculation mode Casida. And this reads in then these two different calculations, the occupied and the unoccupied states, and then it constructs this matrix. So Octopus will construct this matrix and diagonalize the matrix. And I think maybe so then what you can do is you can either use, so what we will do in Notebook, we do it by hand to construct the spectrum from the output, or there's also another run mode, which there's a tool, I think, in Octopus, which can directly calculate you the spectrum. Okay. So yeah, maybe I continue for a few minutes before you guys start with the exercises. So then also the notebook is structured like this. So we will first solve the problem in the electronic case, and then we will add the light matter interaction. So yeah, maybe we do that first. So we introduce what will be different if we now couple light and matter strongly. Okay, so I put it here. We formulate linear response in terms of DFT, right? So now we went from DFT. Now we go to QEDFT. So we put the molecule, same molecule, but now we put it inside optical cavity. Right? So what changes in QEDFT? And then I took this very nice slide from Ita, a beautiful slide where he explains about the framework about QEDFT. So here, okay, so he particularly shows the gauge where you couple now to the vector potential. So there's different formulations. And so this is what we call a velocity gauge or momentum gauge. There's also a different formulation, which is what we call length gauge, or yeah, I think we mainly call it length gauge. So in this particular case, if you have this DFT, I was mentioning it, right? You have a one-to-one correspondence between external potential and now, okay, he uses rho. I used n before to the density. And now the difference in DFT is now that we have sets of variables, right? So we have a set of external variables, which is now the potential, and this J, maybe it's a current. So V and J, which is in one-to-one corresponds to the internal variables, which is rho and the vector potential here. So now the difference we were describing before, right? We were expressing the response function in terms of these variables, the internal variables in DFT. Now in QEDFT, these variables are different, the internal variables. So there's now more possibilities for the functional derivatives. So I will get to that. So this is now what will happen. So now you can see it like this, that if you have your density response here on the left-hand side, and you think about the perturbations, there's now different perturbations which are possible, right? So one thing you can do is you can still tickle your system the same way you did before with your laser. So this is still the same thing. So you can put down, you can write down the dV, the delta V. You still have a response here, connect to that. So that's similar to what we did before. But there's now a different way to perturb your system, right? So this, in a sense, perturbs the electronic system, but you can also perturb the photonic system and not the electronic system. So this is what we do here. So you can perturb the photonic system and then still ask what is the response of the electronic system. So how do the electrons respond to a perturbation now, but a perturbation in the photon sector, if you want. And this is how these new response functions appear. So we still have the electronic response function, which connects perturbations on the electronic part to electronic quantity, the density. But now we have an additional response function, which is now connecting this the response, a photonic response, perturbation in the photonic sector to a response of the electrons, and we call this electron-photon response. And now, in addition, because potentially we can have many photons, we can have many photon modes. So if you just have a single mode, there's only one electron-photon response because there's only one mode which we can change or we can perturb. But if you have, let's say, two modes, there's now additionally, there's two possibilities, right? So we could either perturb mode 1 or we could perturb mode 2. So we would have two response functions, two electron-photon response functions. So that's why there's a sum over alpha up to m. So m being the number of modes in the end which we have. Okay, and then we can do the same derivation what we just discussed. So we can write down the same thing. So that's the Dyson equation here, where we connect the interacting or the many-body response function to the Concham quantities, the Concham equivalents. It's the same or similar to what we had before. Now we have again the non-interacting one with the sum, but now we have these kernels, and now we have additional kernels because of the electron-photon interaction. So we have additional, we call it photon exchange correlation. It's like a mean field term here, like a Hartree, the equivalent of the Hartree. And then we have exchange correlation contributions in this one too. And now additionally, because we can not only, so here I looked only at the response of the density. So we have the same set of equations now, but for the quantity for the photon. Right? So if we were in the length, in the momentum gauge, what Initio wrote down here, where our internal pair, so the other quantity is the the A, right? So then we would have two set of response functions. We would have delta n, but also delta A. And then sometimes, so in the paper which I think I cite, we use delta Q, which is connected to the field, which we use in the length gauge. So this is why I have this additional set of response functions here, Q, which is the other basic variables if you're on the length gauge. So you have these two basic variables, N and Q, and then we get also sets of response functions for that. Again, there's again approximation you have to do. So we have to approximate now not only the Hartree exchange. Okay, we only have to approximate exchange correlation on the electronic part, but now because of electron-photon interactions, we also need to approximate this kernel. And approximations, I mean, Ita talked about the photon-free one, so one could do that. Response function put in the photon-free functional, but there's also other ways which have been developed, which could be used here. Then again, we use Cosida equation, so we map it onto this eigenvalue equation, again now in the frequency domain. Interestingly here, what we find is we find such a block-like structure. So we find now a block, so I call this upper left block here U, which is just matter only, so matter only contribution. And then also the size of that matrix depends on okay, so it's the multiplication of the occupied and the unoccupied states which are considered. Then we get an additional block, which is just to the photon modes. So I call it here light. So alpha, omega alpha is just the frequency of the photon modes. If you just have one photon mode, there's just an additional degree of freedom, additional dimension. And then we have coupling. So okay, it should be this. I think they are complex conjugate of each other. So V and W, where V is just a complex conjugate. But then we have light matter coupling, which we also put. And then again, we can use octopus code. Octopus code will read in. So we do a calculation ground state, unoccupied states, and then it reads in all these quantities, and then it constructs this matrix. The U, I mean, this is the input which we put the frequencies, and then light matter coupling depending on the coupling strength. And then we can solve this equation. Okay. Questions? Yeah.
How the Cosida equation is solved in the program? Do you invert the matrix or?
Yeah, exactly. So in practice, it's just a diagonalization. So you just diagonalize that matrix. I think there's different possibilities to do that too in the code. In principle, I mean, if you write a Python code, you could just use a NumPy library for that. Or SciPy, I think, in Python.
A quick follow-up question. So what is the typical size of the Hamiltonian if I do real materials?
You mean of the matrix, of the Cosida matrix? Yeah, well, that depends. I mean, as always, like, so the size of dimension, right, will be, okay, if we stay with this problem here, right? So you will have the occupied, let's call it NO. So the size of the matrix, right, will be NO times N unoccupied, and then plus number of photons. I think I called it M and M. So that's the size of the matrix. So if it's just electron-only problem, that's just this. But then you see, so if you have a system, I mean, this benzene molecule, I don't know how many occupied states that, but let's say it has 10. And then if you have unoccupied states, depends on how many you want to include. I think in the paper we see you have to go actually quite large for that problem. So I think we use, so one example there would be NO would be 10, and unoccupied, let's say you use 500, right? If you want to be ambitious. So then your matrix size already 5,000 by 5,000, which is still fine on the laptop. You can very easily do. But now the problem is if you add the photon modes, right? If you just add one mode, one photon mode, just one mode, it's fine. But now if we think about these examples which we've seen or which Mark showed, so maybe we need many modes. So if you want to use, I mean, it could be that you need 1,000 photon modes, for example, then you already, your size goes from 5,000 to 6,000, right? Or maybe you want to use 100,000 of modes and so on. And then you are at the limit what you can do. And that's just for a very simple system for this benzene molecule. If you have a more interesting system, which has many atoms, I mean, the size here, I mean, easily can be hundreds, thousands. Of course, it depends on how many atoms you have. Right? So then, okay. So I mean, one thing you could do is, so here we use in octopus we use pseudopotentials. So you only describe the valence electrons. In principle, you could even reduce the number of occupied states further, such that you only include a select number of occupied states, for example, those which are the closest to the HOMO, for example. You could do that, and then you neglect the lower lying ones. Yeah, but that's could be. You want to see one way to see it is it would be a convergence parameter, right? So you start with what you can do, and then you increase, and then you see how much it changes. Yeah.
The matrix generally dense?
Yeah, that's a good question. So generally, it is dense, yes. So there's not really any sparsity which you can exploit. Okay, so the answer to that is twofold. So if you just look at the electronic case here, it is dense, yes. If you have a matrix like this with photons, it may not be dense, because certainly the cavity, for example, the cavity mode itself has a direction, right, with the polarization vector. So, for example, if it's just in x direction, it will only couple transitions which are allowed in x direction. And then some of these off diagonals here may be zero, right? Maybe there's not zero, and so on. So there may be a smart way to exploit sparsity there. And then particularly if you have many modes, that could be useful. Yeah. But yeah, that's not implemented in Octopus. So we brute force solve it. But there's an efficient LPAR solver, which also parallelizes the memory to different nodes. So actually, in the paper, we went to matrix sizes up to 100,000 by 100,000 and did a dense diagonalization, which is at the limit what you can do on supercomputers. Yeah. Okay, more questions? Are you guys all ready to?
For example, the A matrix is explicitly computed.
Which matrix?
Like the A matrix.
In the matrix which I showed?
Yes.
Yeah, well, all of them are explicitly, yes. Yes, well, that's also one bottleneck computationally, right?
Ran for tensors, they're pretty big.
Yes, exactly. So that's just differences of numbers. Yeah, so that's very simple. Yeah, but this guy, K, right? You have to now do the integration over space, right? And it's a two.
Another approach could be for computing the linear transformations. So.
Yeah, of course, but that's what many simulations actually, like chemistry packages I've seen do it actually. But then you only get like the lowest 5, for example, or lowest 10. So you could do that exactly. That speeds up certainly the conversion. Yeah, that's a good point. But yeah, so then here it also depends on, right? In Octopus we use a real space grid, so we have to integrate here twice over the full grid. I mean, other quantum chemistry codes, for example, they use basis functions. So for them, it might be simple to evaluate that. While in Octopus, this will take some time also to simulate.
Then inverting the matrix, you have also the problems of singularities. Maybe.
Yeah, I think that matrix is fine. Yeah, I think it's fine in this case. Yeah, but generally, of course, it could happen. Because yeah, as long as all. Yeah, if you have, okay, maybe it's a problem if there's no band gap, or if you have a situation where you put one molecule, like one electron up, and then want to calculate a Casida equation on that level, because then there's a negative frequency. It could be that you have problems there. But as long as for molecules, it's fine if there's the finite gap, so it just diagonalize it. Yeah. Maybe for metals, yeah, metals could be a problem. Okay. More questions? JC?
I knew it, bro.
All right. Okay, so then we can get to the exercises. So what we do, we start with the first one. So the first notebook is showing coupling just with a single mode. We will see rabbi splitting. Do you have a slide on that? Yeah, so that's something we did in this paper where we derived linear response framework. So we look at the same molecule, benzene molecule, HOMO-LUMO, we already saw, it's around 7 eV. And now if you put one cavity mode at that frequency, and put a specific lambda. So these are somewhat odd units here, maybe for historical reasons. But if we put a weak coupling, we see splitting appearing, and then the stronger the lambda becomes, we see the rubber splitting. So that's the first simulation you guys can do, where we have just tune a signal mode and then see the rubber splitting. And I think you just use one coupling strength. But then if you want to go deeper, you can also use other coupling strengths and replicate a plot like that. Okay, so what does the time say? Yeah, so maybe 20 minutes. And then we go back. Okay, and the notebook is called, let me check. So it's in the Octopus folder. So Octopus tutorials, and then 3 linear response, and then optical spectra from Casida. Yeah, and you may not have any output. Okay, and then you can start from the top, and then we will go first, we will see ground state, unoccupied, Casida electron only, and then there's electron photon calculation. So you can do that. And then you should get a plot like this. And then this is where we can stop, and then we can reconvene.
Johannes?
Just a reminder to start the Jupyter lab with 4 cores.
Yes. So there's maybe this morning you used Jupyter Notebook with just 1 core. So there's different options if you start a server. So just make sure that you use the option where you use 4 cores, because these calculations are a little bit heavy. I mean, 4 cores, it's maybe the smartphone has more cores, but yeah, just use 4 cores so this runs in a finite amount of time. And if you checked out just a single core, then just stop your server and then just check out the new one.
I'm just curious. I remember when we did the Octopus tutorial yesterday, we used a photon exchange functional in the input file. I don't see that. Is it just using the default value of the photon exchange functional?
My assumption.
Okay. I guess I can just go back and check.
What you can do, like it generates the output files, right? You already run it. So we go back to the question.
Yes, of course.
Well, the line where it's coming from, I would have sort of expected. I don't remember exactly where it is, but
Yeah, so where are you? So that comes from the.
But it's not exactly the same. Yeah, but you see,
I think it might be
S here, and then there's a strength function defined, so it's probably in
some prefactor.
So you see it fits the Lorentzian.
Oh. That's what also Mark has there. Mark. Oh, Mark.
So the delta function is then brought by Lorentz.
I'm happy to have 1 photon.
And also when you set up the.
But I think it was all good faith and nobody was upset. It was fine. But I told him I found it.
But I'm pretty sure
You set up with the
I found several
computing.
things that.
Yeah, well, that's the idea. So then in the end, if you include more modes,
Yes,
you get a broader.
I think the discussion yesterday
So
had.
then what we have here, we have just a single mode and a resonance. But now if you have one way to include those, then this mode is brought. So the spectral density of the cavity mode is
Like just.
but then we have to discretize it. So then effectively in the calculation, we have to include not one calculation and not one mode with specific lambda, but we have to include many modes, which then in the weight, the lambda square of that is the same.
Put a bunch of.
Yeah, exactly. So this is a function.
So here, exactly. So here we only have the lossless. Each mode is lossless.
That is negative.
If you
And it gets close enough. It's bounded from below by 0 and it goes to minus infinity.
Yeah, that's okay. I don't use Jupyter a lot. It's like
Never a cool interaction.
Aha.
But
understand use any electron photon exchange relation. Where, for instance, these
that could be interesting. I could see what
You
happens.
can still do it
that are far
sort of like
apart from, of course.
Yeah.
so the FXC goes away, but you still
It makes complete sense. It makes complete sense, but it's a different. Not an operator.
it's like CIS,
It's not a perturbation.
Yeah. Okay.
Right.
even if it is without
Or I guess like the matter is treated at an LTA level, and then the photon. Would the analogy be more like the coupling is treated at like
No.
the equivalent of like Hartree level?
You can think about it that way. So there's actually what's the so people doing molecules like what they call QED. That's basically what they do. They treat the matter with
Show up if you make this approximation.
regular DFT with the photons that they have, and then the coupling to the photon.
I mean, that's always the problem because
like correlated to some extent, but still including some effects.
Yeah. Would there be any like exchange, like photon exchange included with that, or?
Well, it's you still have like electron.
Yeah.
But that's exactly.
Oh, you still have electron photon exchange.
Well, okay, can I?
Yeah.
If you look at our chart that generates,
External charge. This is a hypothesis. Will never be Euclidean.
Linear coupling.
Yep.
Okay. So I think there's a break now on the schedule, but maybe we do like this, that we go over the first notebook, at the first part of the notebook, like for 5 minutes, and then we have the break. You guys can keep working on it, and then we can have more things like this. That's good. Okay, so where are you in the terms of notebook? Did you finish the part? Okay, you got okay. How about the rest? Where are you in the notebook?
I mean, we ran everything and
yeah.
So
okay. So yeah, maybe let's go over the Casida part, electron only part quickly, and then we have the break, so you guys can keep working on it, and then we can reconvene. So just a few points, or just a few things I wanted to mention there.
So we can data change or so when you have change, and you have
all right.
it would be changed all this to instead of coupling.
Okay. Yeah, I just want to emphasize a few things here. So the first thing was that what I was mentioning, right? We have to first run Leo.
What I wrote here is mostly
Leo. Yeah, we continue. Okay. So we first run the ground state calculation, right? So one thing I also want to emphasize that you guys should take a look. One should always look at the output of your DFT calculation, because it will it gives you information. First of all, if you did your calculation correctly, right? So the ground state here, things like you can look out for, it converged, so that's good. So then it gives you information about the occupied state it calculates, and things like total energy. So that's fine. The second calculation is unoccupied. So that's one thing here which we already have to mention, is what I was mentioning before, the extra states. So how many unoccupied states do I want? And in Octopus, this is specified by the number of extra states. So what we do here is, so you see this molecule has 15 occupied states. They're each doubly occupied. And then unoccupied states, we will use 50. Okay, so before we were using 100, but we changed it to 50. So then if we think about the size of the matrix again, here in this particular case, it will be 15. Casida part will be 15 times 50, right? I think it's 750. So 750 by 750, that's not too bad to diagonalize. So this is what we will set up. And then again, you can look at the output. So you see everything seems nicely converged. We have now 65 states, 15 plus 50, 65. And then you see in this calculation, most of them are unoccupied, and up to 15 they are occupied, doubly occupied, and then we go down to unoccupied ones up to 50. So that's what you run first, and then the next part is the Casida equation, right? So that gives us run mode, calculation mode Casida. We set that up. Again, we use these 50 extra states, and then Casida level, Casida theory level. Okay, here it's a long name, but it's a linear response, TDDFT, Casida. There's different options. There's some approximations one could do. We do the full theory, and this is what it calculates. And then again, we always look at output files. So in particular, the important one here is the one, this Casida. So you can take a look at your folder structure. You will find this file like this, which is called, so that's just a folder, and the output file is Casida. So this Casida file. And this is where the information is about our Casida calculation. So then the pole, so this matrix, so the first row here, the energies here, these are the excitation energies. So these are the eigenvalues of that equation, of that matrix equation. And then we get other columns, which are X, Y, and Z, which are the transition dipole moments out of the ground state to that excited state in X direction, Y direction, and Z direction. So this is how this file is structured. And then again, there's last one, it's like an average, that's the oscillator strength. So that's how bright your transition will be. And then if we think about our spectra, absorption spectra, we look like this. So we have okay, so it's just called E here. So the position of the peak, so if this is absorption, here energy, right? Position of the peak will be at E, so E1 first, and then F1 is the amplitude, and so on. So we would have E1, E2, F2, like this. And then important point here is that from this Casida equation in the electronic case, we only get oscillator strength, and we get position of the peak. Right? So then, however, generally, if you look at spectra, they are broadened. So then to get the broad spectra, which you have, is we put some arbitrary, we just broaden these sticks. So we call it the stick spectra with, so in this particular case, with Lorentzian. So that's in the plot script. So you broaden this with Lorentzian. But then the input is the poles and the amplitudes. And then if you look at that very carefully, right? So we can already look here how the system behaves. So we look at transition 9 and 10. So we see, so that's in Hartree. So 0.259, so that's close to 0.26. So transition 9 and 10 is bright. So that's has high oscillator strength in X direction, this guy, and in Y direction, the other one. So these two are bright. And these two are the homolume excitations. So this is the one, and 0.26, if you do calculate with 27.21 or what it is, to convert to EV, you will see this is around 7 EV. So that's the transition we are targeting. And then what will happen if we do the electron-photon calculation? Here, we have to specify where the photon mode we want to put it. So what we do is that we couple it in resonance to that transition, the transition 9 and 10 here, which has the frequency around 0.259. And then for photon modes, we use a frequency. So we tune the resonance, the frequency of the cavity mode in resonance here. So that's what we do here. We put the next one. So that's frequency. Then we have lambda, the coupling strength. So already Mark was talking about that. That's light matter coupling strength. That's the second part. Okay. That's a 0.01. Okay, that's not too strong. That's atomic units. And then we have to put the polarization direction. So here we use 1, 0, 0. So it's the cavity is polarized in X direction. And then if you go back to the Casida output file, right? So we saw that this transition here, okay, it's the next one, 10, actually has a high transition amplitude in X direction. So that's okay. So that's where we can couple the cavity to. That's basic setup of this calculation. We specify the photon modes. Additionally, what we have to do is now if you use photons, we have to use enable photon equal yes. So we activate these features and then we just run Octopus. And then again, we can look at the output file here. That's Casida. So now that's again this Casida file. If we look at what happens around this region here, we see that there's now more peaks. There's 9, 10, and 11, and they split. So there's the one peak goes down to 0.266. So the peaks start to split. And this is basically what we see if you look at the spectra, which you may have already started to look at. There's a peak splitting now appearing. Okay, so that was just a few points I wanted to emphasize. I think there's a break now, so you guys can keep looking at the notebook. If you want, you can already start working further, and then please ask questions. So maybe you can come with some questions, and then we can go over them after the break. That sounds good. Okay, and then we reconvene. I think in 3:45. I think I stole a little bit of a break, but it's okay.
So is the basic assumption here that if like even if 2 photons get emitted during the time evolution, so they are not like an option. Like, is that the physical assumption?
So that's a good question. So that's about that's an approximation.
Yeah,
the construction of the
equation. Because like we are only taking n dimension for the photon.
Yes, exactly. Where you only include one single photon. So you generally only include single.
So should I think of it as like we are only including single excitation, or should I think of it as we are including multiple photon excitation given provided that they are in some non-entangled state?
Yes, we don't have that yet.
Okay.
So we really just include a single photon excitation. And how this single photon excitation is coupled to the signal.
But even if there is a photon creation operator somewhere in the evolution, like in a time sequence, there is no way to avoid it that I'm not going to excite 2 photons because like things are coming down from the excited state. So it can.
So that's the same thing that just also have to linear response. So linear response, you can only do an excitation once.
No, but there is a difference. A linear response means you can only absorb or emit a photon at a time. But there could be like it's a time sequence, so you can emit a photon at t equals t1, and then it evolves, and then emit another photon at t equals t2 to both a linear response.
Well,
but now your cavity
has the linear response here only happens once in time. So that's why you can only emit photon can only be emitted once.
The spoiler that I gave them.
You cannot call it. You also call it adiabatic approximation.
Okay.
So that's on top of that. That's a very good question. I see. So that's the open question. So how can we include?
Because I come from the bottom of the spectrum. And like I have always.
That was only Thomas.
Over the last 10 years, I have always sort of like only quantum information processing. So for me, photons are the hero. The one producing the photon. I don't care about that.
You only slowly get there now. Of course, it's always the better. Because you can't further
so I always try to think of okay, what happens if it emits 2 photons? What happens if there is some entanglement between the modes?
We don't. So you could have entanglement between the modes.
Yeah.
I guess if you have 2 photon modes. Yeah, but like the G2, there won't be a G2. Because we don't have a lot of.
Okay.
So that's the question.
Yeah, it was the same thing. Especially right now with people from Australia. Yeah, it was also like sorry, those 2 spectra.
Yeah, so that would probably, so in the framework which we have, but you could have, it could be a higher order response, like a second order response. So the first process is like that, you say excite, you go from ground state to the first excited state, and then only the second process would be you go from the excited state somewhere. Yeah, but then it would be just higher order.
Okay, and you cannot just do a calculation.
Well, you could do that, but it's not that it's not formally grounded. It's not well formally grounded in that way. So you can always try. If you do it If you do it properly, you will have to start the ground state.
But basically, like the fact,
But okay, it also depends on the functionals because we use these ground state functionals. So that
like ignoring
that's
advantage for us. The FXC is like
use the proper removing it from it's not sure.
Electronic one is still
There might be a way to stop us from putting it
like a golf
you may need to use, or you will have to use
but when you compare to experiment, mainly like
it's like Initio approximation and like photonic contribution at RPA.
Yeah, well, generally it's the I think this is the best
Nobody tells us that we're not allowed to touch the hearing. Exactly, but it's an innovation of hope.
But we are more complete. There's some correlation.
That's what I was going to ask.
I'm from Miami.
Well, it depends on the problem. Like if it's
Enemy.
Well, no, I just reminded you. You talked about last week. Where you have, so there you have different pulses coming in, and then you convert one photon to second order generation. That's a second order process. People explored that. So that's regular.
Out for parking.
But then the problem there is always
I'm like trying. I'm trying to help him. Okay, come back.
You need to do it more. I'll put your name.
No. He starts removing his ring, like this folded ring, and he's trying to put it into my hand. I'm like, sorry. The next step was probably he's going to ask me, like, yeah,
setup is that you the functional depends on the whole evolution of density and the initial state.
Never happens.
So you have initial state dependency.
Yeah, that's why as soon as he starts bringing out that ring, I'm like,
things like charge transfer processes are not
and then he understands.
How do you know that?
I'm sure. That makes no sense. He has all that money for this card. Does it have this card? Like, wouldn't people think that, okay,
like going beyond the application approximations?
They're giving you
what the hell?
That's why the ring is real.
That can't be helped. It's got nothing is a general.
That's so much effort for a scam. Like you have to.
No, but they're doing it all the time. They're doing it all the
time. Beyond what we have in the ground state. The ground state functions, there's many. They may work. Many of them work. Choose more functions for the system.
Wait,
more complex dynamics.
You're looking super rich.
Of course, maybe not as much as for the ground state, but there has been like simple things that we tried. Going to the casino.
He was literally trying to give it to me.
Yeah, now I know. It's so brilliant.
I'm well trained because of Turkey.
So obvious to me that you can subtract.
There's slides on the MQED structure.
Okay, I will ask Mark. Yeah, ideally you will have all the slides of all lectures.
I'm just wondering something. Since the energies depend on the number of unoccupied states, correct?
Yeah.
Do you have to do some sort of convergence?
Yeah, exactly. So that's also why I want to go make some notes because there are some questions. Yeah, no problem.
Again, remember this. Light induced. No.
We're going to write the proposal.
Oh, we do it explicitly.
Yeah, right. But the problem is that
I can remember. So the first question was about double excitations, and now Jonas was asking about.
This is not.
no, I'm just wondering.
Order response, and then you asking about the convergent fractal states. Yeah. So that's the peak. So if you come, so the paper, so in that paper we had 500, and then the volume for this was below 70, it was I think 6.95. But now it's just 50. It shifts up a little bit, so I think it's 7.05 or something like this. So there's 0.1 maybe difference.
I see.
And it's 50. And here for this benzene, it seems that this excitation mixes in some like excitations, like very long range excitations, for which for some, I mean, we know. So for some reason, this molecule does that. This excitation mixes this in. This is why you need to go to a high number of excited states. I think Derek, you met him, right? Derek. Yeah, well, yes. Derek did conversion studies. I think you needed around 50.
Are you talking about Derek Wayne?
Derek Wayne, yeah.
Oh, okay.
We did this conversion studies. I think you need around 500. So 50 is clearly not enough.
Yeah, I see.
But then it scales.
Is it physically motivated? Sometimes, like if you know these Rydberg interactions are there.
Well, it seems that these organic molecules have Rydberg excitations, which are necessary. And these Rydberg excitations, they are better to resolve in the grid than on basis functions, because with the grid we have these tails, or if the basis function they are localized.
You're running this shit on you're crazy.
So that's actually, I think, why the paper from Uncle they were able to.
Because you're not a TA.
I'm not a TA, but he was there.
I know. I am.
Oh, you just downloaded the next version. Martin went. Where is he? But he will be coming back. I think so. You wanted to talk to him? Yeah, because he was interested in the latest stuff that we were discussing. You talked to him?
I'm running into an API error.
Yeah, it's always confusing, nothing works.
No, I think there's a lot of stuff.
If you call octopus.
Oh wait, that's not the problem. The problem is that it cannot open this. But the question is when.
Oh, I'm stupid.
Three and when will the notebooks have it?
It's like yes, like
there you go.
The other side.
I mean, it's linked.
Notebooks are actual
Because
Because you have the right still get you on as well. You have to run notebooks as it's going to until the end. That's really the child not. It's not cool. And then let me know if that doesn't work. But I don't think it's here. When?
That's how it generally works.
I think.
I want to steal it, exactly. Giving it to me, then it's not tasting well.
The problem is in the Qigong page you have a no. I think the problem is
start, and you always get different answers. So they start with the continuum theory, not in Coulomb gauge, and then it is quantized. This is not a good way to go.
There's still some rule. So this splitting, what it does is
but this was where we stopped with last property from the derivation, because I guess this is the whole issue. Start out with the orange gauge, and then go to the discrete setting, and it's clear. I mean, if you make different starting points, then the same approximation will lead you to different results.
Yeah. Well, the signal, let's say the signal
interaction would be just like the usual covered U. Then you would only have this basically periodic photon mode.
Amplitude of 7. The peak will split into two parts equally. First one. And of course, there are always snakes in the grass.
There are definitely snakes in the grass, but at least we can do it, and I think the latest key.
So here the splitting is proportional to lambda.
Continuum.
Squared, lambda cubed, and so on. There's a little difference. So there, if you do change electron structure, you could have.
So I'm running OpenSub, right? I'm running OpenSub. WFAC does not exist. It's not advanced listed.
Well, so, okay. Yeah, that I needed to. Concept itself.
No, just a little. Okay, more than
Now you've done.
Even there's no permanent. At the moment, this concept. So it's going to be the same, but the unit part is different.
Converge the results.
That's the same.
They would depend on the number of unoccupied states. You're so real for that.
I mean, there's this conference open.
No. Yeah. Well, I mean, what you just showed yesterday. I mean,
That's why they pay you the big bucks. You say that every time, and I keep telling you.
You also have other functionals. So I said we only have.
I won't let them do that to you. You're gonna stay right here. I'm going to handcuff myself to you and not be able to leave. You can't kick me out too. Yeah, that's right. Actually, everyone, they definitely can kick me out too, and they won't bring me back.
So for small molecules is fine, but that's what I was saying is
incapable experiment.
diagonals or maybe.
Thank you.
Thank you. Okay, well, it looks like I'm dead again.
Can I ask you again?
Yeah.
Before you twist?
I didn't realize
So the problem, same files that is just generated, the thing is that we want to transfer, but then there is also the problem that
to write these instructions
it
in,
is written
bold red and like for me to see it.
So I guess then the issue is that what we really need to remove is not
Like matter, what are we talking about? This is time result arbus.
Yes.
No,
Oh, no. It's
I am. No, the name of the still what we
They're in there.
Mass realization.
Oh,
It's not found, so it has.
don't say voila, yeah, the thing hasn't.
Now, for bounced it. It takes long.
How far is to hold my R?
Long enough to capture the
Now the idea is you run 7 and then you move 5. Okay. Can you like drag and click?
Sorry, I was too
more like
Well, we can do
the shell, but you can go on the left bar. So that's Control C. So the note
R, so now it's like every R is.
Exactly.
So now it's gotta be like double time that. And
okay, one second.
No, you will see who did it.
This is not.
question.
There's basically a whole.
Watching the cell run. Really, I'm enjoying the tunnel.
Yeah, but there is, I mean, you can choose any output.
You have a counter there?
Yeah, any number.
Now this large
on the so that's studio.
Yes.
Well, that's quick.
How long is it supposed to run?
This makes physical sense.
Not 2 minutes. Okay.
How should that work?
Yeah.
You cannot go to other skills. And now for
Well, you are
there
right.
we go. Alternative results, but only for
We did it.
in the case of type approximation.
The game's not over yet. We can get more points.
Yeah. Right.
So that works.
But that doesn't.
The good stuff with nothing will change anymore. So I could
Music contraction over and then
because obviously if you think about quantum mechanics, we don't think outside
optimized flag inside of it. So if you started running and it took a little bit longer than I thought, okay, well for
now
that was so
there's no quantum calculation. I'm not affected by this infinite scale of my
No.
I did other work during that time, but like I genuinely stared at the thing for a while, and I started like calling up some of my friends. I'm like, hey,
later on. Playing a role, so to speak, but they are not talking in the same way like in freedom.
But then the problem, I mean, but then according to this
my
argument,
entire night was totally wasted on
Not even calculation. Naturally,
to get.
No, I was asking for something
let me
else.
see the different way.
No, yeah, I realize it's not working.
This is my current understanding.
Yeah, because the problem, okay, so
That taught me something. always use an optimal flag. Yeah.
Okay, so then the idea would be, because if you take MQG space,
happy to have 1,000 photons.
now the question is if you can
answer the photon.
Was it working before?
Okay.
It worked on later, and I tried today.
Really? The only thing you read is.
Yeah, it will also not.
But then you can
No, but then you can always
argument is that the radiation you keep in a box with a cavity, and you keep bound states. I mean, not bound, like box states. Those are your continuum.
Okay. How's everyone doing? People are eating snacks. That's a good sign, I guess. Okay, so let's continue. Where do we continue? Yeah, so maybe we go over some questions I got. So I did get questions during the break, so which is great. So one student was asking about the number of extra states in terms of the convergence, right? So if we look at the extra states which you have here, I mean, that's something you can try yourself. Basically, for this specific system, what you'll find is if you do it yourself, so you just change extra states. You could do a convergence study where you have extra states 50, 100, and so on. I mean, the paper, I think we went all the way to 500. And what you will find is that your peak, the HOMO-LUMO shift peak actually shifts. So experiment is more closer to 6.95, so that's an EV, energy in EV. While if you use less extra states, so for 50, I think this is what we are using right now, the energy in terms of EV is a little bit higher. So we see that between 50, so let's say 50 is 7.05 EV, and then 500 extra states will give you a transition energy of 6.95. So you see a 0.1 EV difference. If you're happy with that accuracy, it's okay, you just stay with 50 extra states. But if you want to have a closer agreement with experiment, you can try to increase the number of extra states. And then interestingly, like physically, what's happening for this system is interesting. This benzene molecule, the HOMO-LUMO excitation actually mixes in what is called Rydberg states, which are very known delocalized states, or maybe delocalized is the wrong word, states which are less localized on the core of the molecule. And these states, you need higher excitation, so you have to go to quite high number here. Sometimes you can get away with less states, depending on how localized the transition actually is. In this particular case, if you want to have a position within 0.1 EV, you have to go all the way to 500 extra states. But then, of course, your calculation takes a little bit. One question. The other question, which was interesting, is about two photon excitations. So particularly there about quantum optics. If people think about photons, they think about photon-photon entanglement, where you need two photons, right? Then what was already identified is that the Casita matrix here is just scaling linearly with the number of modes. So that's already an indication that we do some approximation certainly, right? And the approximation we do in this Casita formalism, which is the same what we also do in the electronic case, is that we do what is called an adiabatic approximation. So we only include one particle excitations or single excitations. Meaning on the electronic level, we only include excitations where one electron goes up. Not when we neglect cases where two electrons go up at the same time. And then the same way for the photons, we only include excitations where one photon is excited. Of course, if you want to have two photons, that would be, that you cannot describe it by that. So that would be neglected. So in this sense, we are restricting ourselves with this Casita implementation just to the single excitation manifold. We can only include single photon excitations. So that's an approximation. How to go beyond that is unknown. This is already unknown to some extent in the electronic case. So there one can do things like going to methods like a BSE equation, Bethe-Salpeter equation, And this has been, I think, also discussed by Simona for the photon case. So one could do that, and with that you can also access higher, more photon processes, or you go away from the adiabatic approximation, but then you get a frequency dependency in your matrix. This matrix will become frequency dependent, and then it's not a simple eigenvalue equation anymore. So then that's tricky to do. So there's always trade-off. So that's one question. The other question, then the question was about accuracy, because we talked about comparison to experiment. What limits our accuracy? So is it the linear response, so approximation just to include linear order response, or is it the functional in DFT? So the answer here is clear, I think. So for most materials, it's the DFT, so the exchange correlation potential, which we approximate, which I think I showed maybe the best case scenario, which I've seen, benzene molecule excitation spectra, which is quite accurate. But the moment the material is more interesting, particularly what people study nowadays, if you have correlation effects, then DFT may have some problems. So then this will only inherit in the linear response. So then also the excitation spectra will be less accurate. Yeah, and then there was one question about initial state. So I talked about always the ground state as initial state for the linear response. If one could also use an excited state. So formally, the framework which I showed, that's not possible because it's built in, the ground state is built in. But of course, what one could do is one could set it up an explicit time propagation. They do that. You prepare excited state in terms of occupations. You could populate excited states, occupations, and then just propagate. So then in this sense, the spectra which you will see will also have negative frequencies, because now from an excited state, you can go back to the ground state if you want. You would have peaks there too. But in principle, one could do the simulation, but this is not linear response theory. So it's outside of that regime, and also certainly less grounded formally. Okay, so that was what I noted here. Any other questions about specifically the signal mode coupling for the? Okay, there was one more question. So that's also a good one. So what do we do if we think about the strong coupling now if you're at the cavity, right? So let's say we have our spectra of the benzene molecule. Maybe it looks like this. So maybe this transition here is around 7 eV. If we have a specific amplitude here, okay, let's call it A. So what do we do now if you couple one photon mode strongly here to this transition, right? So let's say now we use omega in resonance. So omega, okay, we usually call it omega alpha equals 7 eV, and maybe the lambda alpha, the coupling strength. I don't know what you want to do. Maybe one popular choice for us is 0.1 atomic units. So what would you get? So you would get Rabi splitting, of course. So maybe we see a split which looks like this. So this would be the Rabi splitting. Maybe let's call it delta. So that's what we expect. If the coupling is weak, this Rabi splitting is mostly symmetric. So maybe if you look at your plot, you would see there's also an asymmetry. The lower polariton, so the lower polariton will, so this is called the lower polariton, called the upper polariton. Lower polariton will have more amplitude if the coupling is stronger than the upper polariton. But the splitting in the weak coupling, the splitting is mostly symmetric. But yeah, what happens to the amplitude was the question. And then the amplitude actually is, so if you there's a sum rule, if you integrate over this one peak at 7 eV outside the cavity, this amplitude will be more or less equally distributed, such that this amplitude from here, the peak here, goes to the other two peaks, to the polaritons, such that the integration, so these two amplitudes sum up to the same. So in this sense, we cannot gain amplitude in strong coupling. So this amplitude will be divided now over the lower polariton and upper polariton. But this is also an approximation. So what we do here in linear response, what is implemented in Octopus is that the kernel, so we call it FMXC, we just take the mean field one. So if you want to call it like RPA type approximation in electron only. So we neglect any exchange correlation. So what we find then is that we can get the splitting. So you see that in notebook. The splitting, I call it here delta, is proportional to lambda, to the power of 1. However, in general, there's higher order processes too, so there can be an effect. Second order, third order, and so on, which correspond to higher order photon processes, which are neglected here. But those then, so this was, for example, what was discussed by ITER yesterday for the ground state. Those effects can actually change electronic structure, and with those, you could also change the amplitude slightly. So it could be that if you, of course, if you do change electronic structure, you could change amplitude or shuffle amplitude differently here. But on the level which we have right now, for the CEDAR case, this is neglected. So that's an approximation. That's also like an intuitive way, right, to think about this. You split the amplitudes, and then, of course, you have the rubber splitting. So that was the first example. Okay. Everyone was successful with the first example? Or was there something maybe which you noticed, or which made you think, which you want to share? Okay. Okay. Yeah, so maybe then we move. Okay, so maybe we go very quickly over it in the sense similarly to what I just did earlier. So this is where we were, right? Okay, so one thing. Okay, maybe I should mention that too. So what we looked at. So this is where the point where we were right now, right? So we have the splitting. We see the rubber splitting. So we have to. Okay, maybe the scale. That's something you can try yourself. So you can zoom in here. You will see the rubber splitting. You can also change the coupling strength. What did we use here? We used a weak one, I think, 0.01 maybe. Yeah, so 0.01. So if you want to use a higher one, right? Okay. I cannot modify this, but you can. Just change it to 0.1, and then you rerun everything, and then you will get a different splitting. Then maybe what you have noticed, if you were paying attention and were reading closely, is what is discussed here in this part. So this is what I mentioned before. So there's the amplitudes, x, the transition. So that's the transition dipole moments. 0 is ground state. So in these lines here, x, y, and z are transition dipole moments out of the ground state to the excitation which we're looking at. So the first excitation, second one, and so on. The x amplitude is this, and then from that we can calculate the oscillator strength. And then the absorption spectra, it's written here. You can write it as a strength function, which is written like this. And then here, as the input, we have the oscillator strength. And then we have what is written here as a delta function. So that's what I was saying before, that from Cauchy equation, we just get a stick spectrum. So we just get the amplitude here, and we get the position, so the pole of the response function. So this will just give us a stick. So we get the stick spectra, and then if you want to compare it, we have to broaden it. And then this is in electronic case, it's done in ad hoc way. How we do it here? We do it with the script. Maybe you've seen this, where we calculate. So the spectrum is calculated here. So in x direction, y direction, z direction with this strength function. So you see we get the poles, and so the poles enter and the oscillator strength. And then the strength function looks like this. This is the strength function, and if you look closely, this is just a Lorentzian. So we broaden each peak with a Lorentzian, and then here we have delta, some small number. I don't know what we choose here. So we use a broadening. Maybe it's defined above, but we use a small broadening delta, which is then just gives us the width. And this is just chosen in an ad hoc way. So people just make something up such that the spectrum looks nice also then compared to the experiment. But there's nothing more. And then, of course, in physics, or like physically, what contributes to these processes, such that in experiment, these peaks are actually not broad. Some dissipative processes could be electron-photon coupling, for example, but also in the cavity could also be intrinsic line width due to the structure of the electronic field. So we will get to that in a second. Okay, exactly. Okay, so now we can go back to the talk. Okay, yeah, so we have already successfully done the first example, right? Just strong coupling with a single photon mode. So here we had this problem here. We have this Casita spectrum, and then we just choose a single photon mode around 7 eV with some coupling strength, and then we see the rubber splitting, right? So maybe we are happy with that, but it's just a single mode. So certainly nowadays, if you publish papers, people will start complaining. Maybe we should look at more than one mode to more realistic, to model the cavities more realistically. So this is now why we want to look at the second example here. So in particular now effects like dissipation. Okay, strong coupling we can describe by connecting what we discussed or what Mark was discussing on Wednesday. So how do we do that? Or how do we think about that? That was I already showed. You guys did that already. So that's just a brief summary how we can describe dissipation or how we can think about dissipation. So if you think about the cavity, the optical cavity with coupling to one molecule in a perfect cavity, right? We would just have a single photon mode. We get splitting in lower and upper polariton. There's just two peaks, splitting into peaks. However, the cavity may be lossy. So then here, while here, the cavity also, in a sense, only has one state, just one photon, which is sharp resonant. So the spectral density, we call it, of the optical cavity is sharp here, just one state. In lossy cavity, for example, you could have leakage out of the mirror. Also was shown by Professor Kono. This peak here, the spectral density of the cavity is not sharp, but it has can have a distribution by itself. So the spectral density also can be brought. So if we plot the spectral density, right, of the cavity, while a perfect cavity, it would be infinitesimally small. Maybe here we choose again 7 eV. In reality, because we have losses, the cavity mode itself, maybe we call this J, maybe here again, okay, maybe we use frequency here, it will be brought. And then how we can this represent in the computer is that we would have to discretize. So then this we would have to include by many modes. So then we would go from a calculation where we only have a single mode to a calculation where we have to accurately sample where we have to accurately sample that spectral density. And we can do that by including many modes. So then we can define a mode spacing here. Maybe we call it delta omega. And then depending on how, okay, depending on computationally what we can do, but also depending on the setup, we have to choose how many modes we want to include. Then again, so this is also what is shown here. So if you have less losses, for small losses, the spectral density, or here we call it spectral response, the cavity is sharp, such that in the limit of no losses, it would just be infinitely sharp. So we only need a single photon mode. But if we have many losses, the spectral response of the cavity can be broad. So we have to include more than one mode in the simulation, potentially many. And then also if we go back to what we've heard in the very beginning already from Professor Kono, how we can think about strong coupling and now dissipation, right? If we have now a specific peak here, we want to couple to it. If we now start on this axis to increase the light matter coupling strength, what we will have is that we will see now the strong coupling appearing. So we see the rubber splitting appearing here. Clearly there's strong coupling, there's hybridization of light matter. But now in the opposite limit, if we now have strong coupling, but increase the dissipation, meaning that if we go back to the slide, the losses become more and more. So this spectral response of the cavity becomes broader and broader. Then in this sense, we can go down again from the strong coupling to a limit where we are effectively again recoupling. And then the coupling strength here, the light matter coupling strength, so these lambdas are still the same. So the lambdas here are the same here in this in this simulation as in this one. But now we have more photon modes and the spectral response of the cavity is just broader, such that we increase the dissipation. And then effectively we are again in a recoupling regime where we are not able to clearly resolve the strong coupling. So if we talk about strong coupling, we always have to talk not only about these coupling strengths, which we call lambda, but we also have to think about the dissipation. And a way to include this dissipation is by connecting to the macroscopic QED approach. That's important. And only if the Rabi splitting is clearly appearing, we can talk about that our system is in a strong coupling, or what was already used, different nomenclature. So maybe if we can be even stronger, maybe we can achieve the ultra strong or the deep strong coupling or the other limits too. But we have to overcome. Yes.
What determines the sort of rate or strength of dissipation?
Well, okay, so there's different ones. So that if we just, okay, so if we here just think about the mirrors, it would depend on the losses of the mirrors. Could be just intrinsic effects of the material, if we have gold or silver mirrors. But you could also go to setup where we have now structural. You could have DBR, so you have more than one layer. So then this would also reduce the losses. Things like this. So it depends on the cavity, so okay. The cavity design. Yeah. Yeah, and then also I think if they can also cool down. So if you want a very good cavity, you can also cool down, and then you have superconducting mirrors, things like this. So there's ways to improve it, to improve the fidelity, it's called, of the cavity, to go to such that if a photon is emitted, it bounces back and forth a lot of times.
Yeah.
So that's one measure to measure the quality of the cavity. How often a photon would bounce around before it becomes lost.
Yeah.
Okay. Other question? All right. So now we want to go. I was already teasing that a few times. So we want to go back to how do we describe the cavity more accurately, and how do we interface that then in our linear response calculation. So for that, we go back to macroscopic QT. So this slide, which Mark already showed on Wednesday, where he defined these different steps. So for macroscopic QED, for MQED, we only need to determine the epsilon and the mu, so the dielectric constants. Once we have that, from that we can determine the Green's function. So this we already did in the notebooks. Mainly we did it for analytic models, but you can also use, so exactly with that. The notebooks will be about that, analytical solutions for simpler geometries. But in principle, for arbitrary geometries, you can use just existing software packages. Maybe very popular one is COMSOL. There's all the other ones which can solve these finite element methods. And then once you have that, basically because it's ready to use macroscopic QT, we can feed it into QEDFT. So yeah, so how do we do that? So this also he showed already. So this is what we need. So here's our Hamiltonian. And then for us, how light matter couples is via these constants here, lambda and omega, coupling strength and frequencies. This is how so Q are the displacement of each harmonic mode, quantum harmonic oscillator, and then R is the dipole moment. So we need to determine these somehow from macroscopic QT. And this is, okay, the reference missing, but we had a paper together with Mark where he outlined how to do that. So once you have the photonic, the Green's function for your geometry, we talked about that, calculate the electric field at that point. And then you can just convert electric field. You plug in the electric field here, and then there's a simple connection between the electric field and the coupling strength here, which we call lambda. And then I think this guy is the same as this one, yeah, where just we use the lambdas here. Now for macroscopic QT, where we have the photonic Green's function. And then what we will do in the next example is that we look at the specific geometry. We have a spherical cavity, so you guys already looked at that. You analytically calculated a spectrum like this. So you see, depending on the setup on, I think the R is the longer one, how big this spherical cavity is. We see different resonances appearing. So for 350 nanometers, you see there's at least, so there's 1, 2, 3, 4, 5, 6 resonances, sharp resonances. So this would be a cavity which can host 6 modes. And then, of course, there's a tail at the +1 frequency. If we reduce the size of the cavity, we go to 140, you see there's only 2 modes contributing. And then if we look more closely at each of these modes, we see that they are actually not perfectly, because the system now is, so that these epsilons now, the system can be lossy, epsilon 2 and epsilon 3. So the peak is not infinitely sharp, what I was discussing here, but it actually intrinsically broadened. So this is what you can already, I mean, these look very narrow on the screen, but you see for these ones, it's somewhat broad. And then in the example, what we will show, what we will use is, so if we zoom in, okay, so I think this is neither 140 nor 450, so I'm not sure which radius is this, but maybe 60 nanometers, something like that. So here he played around with the losses in the cavity, so that's the gamma. So if gamma is 1, which is the true gamma of gold, you see one of these peaks is somewhat, so that's the blue one, is quite sharp, but it's not infinitely sharp. So if you want to sample it in our DFT calculation, we would have to discretize it, and would have to sample this range here, include few modes, and then the lambda. So in the end, what will happen is, okay, I don't have a slide for that, but the correspondence between the setup where the system is infinitely sharp is such that the integral over lambda squared is conserved. So there's a sum rule again, meaning that if you change, if you have a specific lambda square at just one mode with a specific lambda square, if you change that and you want to keep this effective coupling strength to a situation where we have many modes, you have to have many modes which have then a lower lambda, such that if you sum again or if you integrate again over this lambda distribution here, you will get the same lambda. So this is how it's conserved. So then all these lambdas here are effectively the same. So you see then if it goes up here at the highest point, it will go up in the, so if it goes down in the highest point, in the maximum, it will go up in the tails too, such that the lambda is conserved. And then depending on which which loss factor you choose here, if the loss is higher, it gets broader, so there's more losses. And if the losses go down, the peak gets more and more sharp. Yeah, and this is now how it looks. So the first thing, I think I told you that you can already start with the rest of the exercises, but there's one caveat which you need. So we have to go back to notebook 7. It's called, so that's in the notebook folder, go to notebook folder, and then you go to notebook 7. And then, okay, so maybe we do that together. So it's this one, notebook 7, describing the real cavities. So this is what you guys already looked at on Wednesday. So just as a reminder, we use these dielectric analytic forms for the dielectric constants, either the Drude model or Lorentz model. And then we calculated the spectral response or the spectral density of these cavity setups. And now if you go all the way down, maybe some of you did that already. There's the part which now gives you or which outputs these modes into a form which Octopus can read, such that you can read it into Octopus. And then in the end, the structure is simple. So that's just a function now which calculates the lambdas. So that uses this formula which I just showed, which connects lambda to the electric field. That's the first part. Of course, here it's a little bit more tricky because there's so many conversion factors. It's all the units to get the unit right. In the end, we want to have the units, atomic units for frequency and atomic units for lambda. That's why there's a bunch of conversion factors. So that's the first part. It gets, so it has this function. This is what we use here. So we loop over, so we want to do calculation. We have different gamma factors, what I was just showing. So these losses, so we go down in gamma factor, so it becomes less lossy from 1 to 0.05. And then we calculate these. So we use a metal which is similar to gold. We have to shift it a little bit because of resonancy. But then we calculate the lambda, and then we output the lambda. So we feed the lambda into this function here. And then the output is basically this function here, where now we have a file which has these different entries, the frequency, the coupling strength, and then the polarization direction, just similarly to how it was in the input. And so that's the first step, that you guys go to the very end, and then you just run this script, and then it will output. We can look at that. So it will output these files. And then if you look at the spectral density here, what is plotted here, now we have a cavity. So we choose, okay, so we chose a cavity setup of where the resonance is. So we also chose the epsilon such that so that's the transition which you calculate with Casita. So you see, okay, so from top of my head, I was saying it's 7.05, it's close, 7.06 or something like that. And then the cavity is changed such that one of the peaks is in resonance to that transition. And then we just change, just to illustrate, we change the damping or the loss factor on the cavity. So here 1 is the one which I already showed. It's a bit broader here, but you see the axis here is just 0.15 eV, so it's quite narrow, 150 MeVs. And then if you go down, the peak becomes more and more narrow. So the cavity can host more narrow peaks, and it becomes loss. We have less losses. So then if you look at your notebook, okay, I have to change the path. So if you run that, you go to notebooks. Okay, so it will look a little bit different. You see I have a bunch of them, but maybe we just open one. So we'll see, we will generate files which look like this. So there's an identifier in the beginning, which says how many modes are. So Octopus knows how many lines it has to read in, and then how many rows there are, just 5. That's always the case. And then we get files like this. First one is frequency. So we find, so there's a 3. So these photon modes are 3 times degenerate because we have them in X, Y, and Z direction, and so on. So here we have 1050. I think 350 in each direction. And then what you need to do is that you need to copy this file from this folder. So you can do that maybe with the terminal. So you just copy it to your Octopus tutorials and then to the linear response to this folder. And then you can use it in the Casita calculations. What's the other one? Okay, exactly. Yes, so let's go back to that. Okay, so I didn't have to show that because that's the structure. So then what we do here is we just sample it. This is also why we want to have it narrow. It's also just for the sake of demonstrating the approach that we want to, of course, the more modes you have or the finite you sample it, the bigger your size of the Casita matrix becomes. We discussed that. And then the calculation will become more and more heavy. So this is why we restrict it. So now we have 1000. So we have the matrix size in the end, it was 750 before. So 15 times 50. But now we add these 1000 modes. So we have 1000. So less than 2000 dimensionality of matrix, which is still very, very much fine to diagonalize. Okay, and then the goal of the exercise is to get something like that. So that's what we had in the paper with Mark. Now, if we change, so that's the spectral density of the cavity mode. If we now change the losses, we can go from if it comes so if the losses are high or higher, I mean that's not really high, but if they are higher, we see that the strong coupling, the dissipation, the losses are too high. We don't find the strong coupling regime yet. If we now go down in terms of losses, we can more clearly resolve the splitting. But then you also see the splitting is still quite small on that scale, but we can resolve it here. So that's the goal of the exercise. And then there's other things which in the paper which you have. So one thing to increase light matter coupling is we discussed that along the collective strong coupling regime. So if we we had just had a single benzene molecule, we could put more than one. In the paper we saw that we see splitting more clearly resolved. So that's square root of n, what was also came out in the paper throughout the school. The square root of n behavior in terms of rubber splitting, because it scales as lambda. it's the lowest order, the more molecules we put. So that's also what we can do. Okay, that's already the next example. So yeah, so yes, so I mean, some of you guys may have already worked on it, but maybe with this additional insight about how to get the photon modes, you can continue working on that. And then the exercise will give you only one example, maybe the 0.05. So you can also try, you can generate other photon mode files, and then you can also calculate the other the other spectra if you want. Okay. How's everyone doing? I think we're losing people, but we're almost done. We're almost done.
No.
Okay. So yeah, so I think hopefully by now you guys were able to just, I mean, if you just ran the notebook, right, it should run through. And then the last example we were looking at was this spherical cavity. So, okay, so my side looks a little bit different because we've changed the folder structure. Now, if you look at the photon mode file, this is the one which we have. Again, we have these 3 modes that it generate, and then we have 1050 right modes in total. And then if you run it, so here the plot script is now a little bit different from before. So before we used this function, the strength function, which was fitting the Lorentzian. So in this plot here, we don't do that. So we just plot the sticks. Okay, just one like this, right? So we just plot the sticks. And then what you see, if you just plot them next to each other, is that's the plot. Okay, it doesn't show yet. Okay, that was the other calculation. Yeah, so you will get a plot like this. So we now see rubber splitting. They're splitting into 2, right? So that's the distance between these 2 peaks will be rubber splitting. This will be similar to the paper which I showed, the plot from the paper. But now what we have is that we don't explicitly put the splitting, the broadening. So if you see here, so what we plot is we just plot frequencies, and then we plot the oscillator strength. So we sum them in all directions, but then we just plot them over each other. So you see here, the peaks are broadened, and they're intrinsically broadened. So in a sense, this is a natural line width for this specific cavity, which is already broad and it's not sharp anymore. Of course, what you could do is you could broaden it by hand to make the plot smoother. So then you will get a plot which was in the paper. But then the essence here is that now we don't have to put this line width by hand, but we automatically get it from our calculation. So here in this case, we get the effect of so this is what is called natural line width. So due to the electron-photon interaction, there's a broadening in the spectra, and we are able to capture that now because of the many modes. And this broadening is due to the dissipation, and this dissipation is now due to the dissipation in the cavity. So this could be losses, whatever we discussed, for example, through the mirror. So that's the effect here. And then what you can do at home is that you can change the coupling strength. If you change the lambda, you will see that if you reduce it, you will go down to the weak coupling regime. In principle, you could also make it more strong, and then you would get a bigger rubber splitting. So you would be able to access the ultra strong coupling limit. Okay, that all makes sense. Questions? So then, yeah, if you think about this interfacing macroscopic QED with TDDFT here, that's fairly straightforward. We use macroscopic QED to generate this photon mode file. So we call it photon mode.dat. And then this is read in from the input structure, input file in Octopus. And then this considered in the Casida equation here with additional rows and columns here. So the size gets bigger in the Octopus code. But then the Octopus code takes care of diagonalizing it and outputting it in this Casida file. And then there's one more example. Maybe some of you I've already run it. So there's you call it bonus. There's a lifetime calculation now for one-dimensional cavity. So you can also run that. Now we have many modes. So here in a sense, we also use, so we use also an analytic form to calculate the modes. So in a 1D cavity, right? So if you have a 1D cavity, the modes are just the lowest order, just a sign with no node, and we have a sign with one node, and so on. So we just include a finite number. So we choose the length of the cavity. We choose a finite number of modes. I think again here we use 1,000 modes, and then with that you also get a broadened spectral density for the cavity here. And in the 1D cavity, you will see intrinsic line width, so natural line width of this transition here too, inside a one-dimensional cavity now. So I was asked here about this plot. So you see here that there's these sharp features. So that's actually positions. So there's many resonances here next to each other, but there's some additional resonances. And here we only couple in x direction, but the molecule is three-dimensional. So some of the excitations have amplitude in y and c, but not in x. So in x, the oscillator strength will be 0. These transitions fall for some reason between the 6.6 and the 7.4 here, right? So this is why it's plotted here. So we have these transitions from the coupling to the cavity, which is the solid line here. But then we have additional peaks, or additional, it's not a peak, but additional poles, which have no oscillator strength. So this one, this few, which are 0. So this is why it looks discontinuous. But in a sense, you could neglect it because it doesn't couple, or you just plot it via points, and then you will see a somewhat smooth behavior here. Okay, so that's these examples. And then one thing which I wanted to mention in the end is so that this linear response framework is not only relevant for calculating excited state properties, but there's also actually, they also give a way to calculate or to construct exchange correlation potentials for the ground state. And this is done via the so-called fluctuation dissipation theorem, so you can do that. And if you're interested, you can read more in this paper. So there's we have now a series of paper. So that's orthogonal to what the function which Initio was discussing, the photon-free one, which gives us so this one gives us a different route to construct exchange correlation functionals now using the linear response framework, meaning that we need ingredients such as the electron-photon response functions. So if you're interested, you can read more about that in these papers. Okay. Questions? Everyone was able to run the notebook? Everyone is tired? Looking forward to the weekend, I guess. Okay. So yeah, just to wrap this up. So we discussed this. So that's the calculation. Now in the one-dimensional cavity, so this bonus calculation you can run. So we see for this pi star transition, intrinsic broadening, natural line width. You get these additional poles here, which are electron only. They don't have a transition amplitude in x direction. So here we plot it like this. And then you could do similar things now because the one-dimensional cavity, we have this in all transitions. So that's the lowest one, pi star. There's also one around 10 eV, which also will have an intrinsic line width, depending on the amplitude there. So you can compare the numbers here. So they're similar actually. Okay. So we did that. So one thing, okay, just very briefly, one thing what is useful for to calculate excited state properties is also for photochemistry. So going all the way back to chemistry, photochemistry, if you excite to excited state surfaces, system relaxes. So we need to access these excited state surfaces. That's just one simple example. And then these excited states, we can properties we can calculate with linear response. This is what we did in one of the papers. And then we're interested in how this changes in strong line matter coupling, then which gives us an idea about photochemistry in cavities. And then we use Casita. So this is the ground state surface. We use Casita to calculate the excited state properties. So that's just a single excitation manifold. So then the excitation would be here around, what is it, 4 eV. You could excite. And then there would be some dynamics. So here there's an avoided crossing. There's some complex dynamic going on. So now inside the cavity, so with this Casita linear response, we can look at how this would, so what the strong coupling would emerge. So if we zoom in into this first excited state landscape here, this part here, and now we add a single photon mode, we get an additional pole, an additional surface. So as you see here, so here we have an addition. So here we only have 2 surfaces. Now we have 3 because we have the photon mode. And then depending on the coupling, we can either change the minima. So the process would be something like system was excite here. If there was some oscillation, and then it would go down here, for example, or it would go down here. That different pathway is possible. And then with Casida, TDDFT, and with this in strong coupling, we can change. Either make this minima on the right-hand side deeper than the left one, or we can also crunch it depending on the situation. So calculations like this then are not only for spectra. So these Casida simulations are not only useful to calculate spectroscopic quantities, but we can also try to more directly access excited state properties. So for example, here for photochemistry. And then there's a different or like a somewhat rich possibilities what can be changed using optical cavities. And then the basic idea is always that you replicate surfaces, you have an additional degree of freedom, and then these surfaces hybridize. And now this is over the distance of the CO molecule, the CO bond distance. So then depending on how you tune the parameters, so it's just a single mode, you can get different effects. So the cavity can, in this sense, also change photochemistry. Okay, so that's basically it. So this is what we did, so quite a bit today in this afternoon session. So we learned about Casida, linear response, just for the electronic system. TDDFT, we discussed connection to Casida. We added the photons. This was all based within a DFT framework, so we exploited this one-to-one correspondence. For DFT, we have n to potential, so the density to the potential. Now in the cavity, we get set of variables, so this is why we also get more response functions. So we talked about these light matter response functions or electron photon response functions. And then we looked at a bunch of exercises. Casida just for electrons. Single photon, we found rabbi splitting, lowered our polariton. And then we connected to macroscopic QED, to what Mark was discussing on Wednesday, where macroscopic QED allows us to extract the parameters, frequency, lambda, and how many modes we need for more realistic cavities. Particularly, we looked at a circle cavity and a one-dimensional cavity. And then we also find strong coupling, and we are able to tune the parameters. And then just in the very end, I want to emphasize, so if you are interested in taking your data home, do that now. So because the cluster accounts, they will be closed after the school. So one way to do that, you could create a tarball of just a folder, and then just scroll through. So that's interactively. You could, okay, that's here. So if you do that in the terminal, you will find there's a new tarball created, and then you could just click here download and download it to your laptop. And yeah, you should try to do that either now or a little bit later, because they want to close the cluster accounts tonight. And then there may be possibilities to get access, but just do it now. All right, so that's it from my side. And then I think Simone and Ankel have a few words. Okay, maybe if someone has some questions. Now we are waiting. Yeah, everyone looks tired.
Looks like it's one of
Don't see that before.
No.
Okay. Good. It's a little bit late, but I think it's time to close the school. I hope you all enjoy it and you like the last 5 days here with us in the Flatiron Institute, and then that the school has provided you with a solid background of something that you can work more at home. Then we didn't put any homework to do, but maybe in the future we should consider to add it. Anyhow, the point is, on behalf of all the organizers, which we are the 4 of us, we thank you for all your efforts in following the school. I hope you learn, and please feel free to ask any question or any comment you have in the days to follow, and weeks or years to follow, depending on the time scale that takes you to solve the problem. But there is one thing that is really important. This school has been possible because of the background work of 2 people, which are in the back, which is Diane and Anne. This would not have been possible without them. I know that everybody says always the same, but it's true. That without their work, this would not have been possible. From the setting of the web page to getting all of you coming to all the things that you see around. And I think it's important for the smooth running of the conference and so on. I think with that, I thank you. We will keep with our ideas to keep rotating these schools between Europe and United States. And in between, there will be, at a given point in life, a book that you will have access to, will be open access. And this is the global idea. And then before closing, I will pass the microphone to Simone and Rugi, that they wanted to do something more physical.
We'll be available for more questions, but one thing that just came up to my mind is that we will send you a questionnaire to get feedback, so that hopefully you can make it less painful for the next generation of the school, if it was painful. Or you can also tell us what was good, so that's something that we will consider and will keep. And is there anything else to add that you want to add?
I think it would be super if you give us feedback also on the slides and lecture notes, and also on the explanations, because since we tried to wrap this all up in a book, I think we realized also in writing the book, because there are very many people involved, that there are very different perspectives on the same topic. So the more input we get, the happier we are, because we can then subsume this and can also explain it better. So that would be super.
Do you want to say something?
Maybe the only thing just came to my mind is with the GitHub repository or the GitLab. So we will this will be kept open access, so you can check anytime. And I think also there's an internal one which we may also access, open access. Yeah. So you can check. You can go back to look at the slides. We will upload the slides. So this will be there. Any feedback is welcome. Jason.
Will the particular implementations of like Octopus and like all the stuff that is required for the kernel environment also be available open source, or no?
Well, maybe we should discuss that. Yeah. I mean, in principle, we could do that, but I'm not sure how helpful it is if you don't have access to the Flatiron cluster.
There's just like a list of the stuff that is necessary to run the stuff.
So the build script is open access, actually.
Oh, okay.
So that's already online. I mean, we can link to it and make it more explicit. Yeah.
That's good feedback. Okay. I think we can thank also the TAs, maybe.
Yes, definitely.
Yes.
And the last.
Yeah, so there's Lucas, there's Mohammed,
and then is Leo. It's important. Everybody has contributed. Okay, all right. Good. Then thank you.
Yeah, so we will be around, so we should thank you once again.
We thank you.
And, so you're free to go, but if you have questions, we'll be here and we can also discuss them all together. But from now on, you should feel free to go if you want to. But if you want to know more, you can stay.
Want to know more?
Or be more confused. That's also an option. You don't know what you get if you stay. But yeah, that's it. That's a wrap.